All right, this is part two of my multiple regression section of the 103 series. So we're resuming on the concept of a multiple regression, and we want to know how we would do like hypothesis testing on a multiple regression. So if you've watched the last video, it's not a surprise that in a multiple regression we would do similar processes of the single regression. So we would say we would choose a specific coefficient, and then the null would say that the coefficient is insignificant, while the alternative is not significant. And then the t-statistic would pretty much be the same. All right, so let's look at our first example, where we have once again income and price, so multiple regression. Let's say we want to test if a raise in income of +2 is more effective than decreasing price of -2. And so in this case, we would use a linear combination of parameters as our inference. Just a second. All right, so our null hypothesis in this case would be 2 beta 2 minus 2 beta 3 is greater than 0, because again, if this is greater than 0, that means a +2 income in income is greater than a -2 decrease in beta 3. And so we're subtracting that off and see if it's greater than 0. And if it is, then that means the raise in income is more effective than decreasing the price. I think I made a mistake here, so this should actually be the alternate hypothesis. And then our null should be that a raise in income is more significant than a decrease in price. So the null is that this is not true, essentially. So a raise in the income is not more effective than decreasing price. And then the alternative is trying to reject that, which is saying a raise in income is more effective than decreasing the price. And so because we're using multiple coefficients here, or we're trying to find the result of the food expenditure, we have to use a linear combination, what we denote as lambda. And then the standard error of lambda is all of this right here. And we're doing that whenever we're trying to, our null hypothesis or our hypothesis testing involves the y, not just beta 1, beta 2, and if they're significant and whatnot. So if we want to like find the results. Okay, but then everything else, we find a t-distribution table for the critical value based on the sample size, type of test, and our confidence level, so like 95%. We would use a one-tail test for this because we're saying it's greater than, not equal to 0. And so if the t-statistic is greater than the critical value, in this case it's not absolute value because it's not a two-tailed. So if it's greater than, we reject it and we say that the raise in income is more significant than decreasing the price. All right, so let's go to another regression function example. So in this case, we have the consumption of pizza and our variables that can potentially affect that. And notice how the coefficients are negative in this example. So as we eat less pizza, or we eat less pizza as we get older, and then we also eat less pizza as we get richer. So I don't know how much that makes sense. How much that makes sense intuitively, but let's just go with that example. So the problem is, what if older and richer people, so if a person is relatively old and rich, they'll based off this equation with minus and minus, they'll eat less pizza in general. But what if they actually further reduce their pizza, knowing that they should eat less pizza based off their age and income, and so there's like a further reduction in their pizza consumption. And the answer to that is we can add an interaction variable. So we have the same regression right here, but then we add an interaction variable given by the coefficient of minus beta 4 and then age times income. And so this is important because now this accounts for people that even further reduce their pizza consumption despite them getting older and wealthier. So when we're measuring the slope of age and income, or I guess a change in y, in this case it's pizza, in respect to age or income, we have to use the partial derivative rule, where let's say we want to find the change in pizza in respect to age, then it would be minus beta 2 right here. And then we would, right over here, minus beta 2, and then we would disregard this because it doesn't have an age variable. Right here, we would say minus beta 4, and then extract the age variable because we're deriving in respect to that. So this age right here becomes a 1, and then the minus 4 beta times income is left over. Similar to the pizza, change in pizza in respect to income. So we went over the fact that a single coefficient test in a multiple regression and a simple regression is the same. But what if we want to test multiple coefficients at the same time? So in that case, we would do what we call a joint hypothesis testing. So in an example, we would say both the beta 1 and beta 2 coefficient are 0. The null would say that, and then the alternative would say beta 1 or beta 2 equals 0. And so if we're giving this function here, food expenditure, income, price, and then price squared is kind of the difference, our null would say, we could say that the null of beta 2 and beta 3 is 0. And then the alternative of beta 3 and beta 4 not equal to 0. In respect to price, we're just ignoring income. It doesn't have to be we don't have to test for all coefficients at once. And so what we do is we make two different models called the unrestricted and the restricted. In our unrestricted model, we usually would reiterate the same model as what we were originally given. So over here, food expenditure, beta 1, beta 2, beta 3, beta 4. But in our restricted model, we would write it based on our alternative hypothesis, or our null hypothesis that beta 3 and beta 4, the factors, the potential influencers of food expenditure, which is price, those are excluded because our null says those are 0. So in the restricted model, the function is just the expenditure is based off our intercept and our income. And so because we make two different models, we also have to, or essentially we're creating two different regression functions. And so we create two different sum of squared errors as well. R short for restricted and U short for unrestricted. We'll denote that in our error squared as well. So error hat I R square, and then error hat I unrestricted square. And then recall that because our restricted model or our unrestricted model has more coefficients, um, that will actually more always the more cases than not. In fact, always it will have a higher standard sum of squared error because, or sorry, our unrestricted will have a lower sum of squared error because we have more variables that are trying to predict food expenditure. So in our least squared or sum of squared error function, we subtracted from more variables, if that makes sense. Um, so I guess another way to make it clear is the more coefficients we have, generally the lower our errors are because we have more predictor variables. So almost always our sum of squared error in a restricted will be higher, and that's important because that's actually determines how we calculate the F statistic, which we're gonna find a difference of them divided by J, which is the number of restrictions in the joint hypothesis. So in this case, our number of restrictions will be 2. So we have beta 3 and beta 4 that are restricted in our model. And then all of that divided by the sum of squared error of our unrestricted, so the whole function, divided by the degrees of freedom. So n minus the number of coefficients in the unrestricted model. That is key. And then like the t distribution, we'll use the um, chi-squared aspects of it because that's how we do it for all test distributions. We don't use a normal distribution. That just assumes we have an unlimited sample size. And so this is how it will look like. Once again, recall the central limit theorem. If we have a low sample size, it will look nowhere to a normal distribution. It will be skewed to the right because we are squaring our chi-squared, so it will never be negative. And as our sample size gets larger, it will become closer to a normal distribution. Note that the F statistic, although we use it to so the simple linear regression similar to it, the F statistic also compares it to the critical value determined by our sample size, the type of test. In this case, it's a two-tailed because we are testing if these have an effect or not necessarily if they're positive or not or negative. And then our confidence level, so like 90, like 95%, whatnot. And then, like I went over, we can use the multiple regression joint hypothesis testing for a single hypothesis test. So let's say we want to just test if a single coefficient is significant. If we want to find out if income is significant or not, our null would say it's not. Alternative would say it isn't or it is. And then we could actually find the F statistic using this formula right here to reject to determine whether we should reject the null. And so mathematically, we actually get that the t squared, the t statistic, which is used for a single regression, if we square that, we actually get the F statistic because they generate the same p-value. So essentially, the process is the same, except the catch is that the F statistics only works for a two-tailed test. That would make sense because in an F statistic test for joint hypothesis testing, we're only testing if the coefficients are significant or not, and so we would have to square it as we see in the denotation here. Okay, that is all for multiple regression. In the next video, I will go over how we can actually get like these correct functional forms. So how we know if age and income is the best indicators for pizza, um, how we know if income and price is the best determinants for food expenditure, stuff like that.